Thanks for your time and everything. So maybe I think we can, if you have time, we can take like 3, 4 questions, quick questions. Is
Sure,
it
sure, sure.
okay for you?
Sure, sure.
Sure, sure. So I mean, floor is open for questions. So Usman, physically, I think you can moderate if someone has questions. So you can just bring them close to the, you see, close to the laptop. They can come and then ask a questions. Yes, Usman, please, physically you can moderate, and then we allow the online participants. Yes, please.
Sir, I'm here,
Sure,
sir.
they are. Oh, yes. They,
Sir, Isma has raised question.
no, no,
Invite
not
him.
then we go to the online people. If there is some from
There's a couple
this,
of hand.
yeah. Okay. So I think we can go ahead with those who are on available online. So Isma, maybe go ahead.
Thank you so much, Dr. Trevon, for a very nice presentation and giving us a deep insight of AI. So my question is related to inverse design. So whenever we have multi-objective type problem for inverse design, so we somehow suffer in terms of computation power because we cannot go very high. If we just like a conventional design procedure, when we do some simulation for proof of concept for small meta surfaces, and then we can scale up. Can we have some method for this which are somehow work in the same way in inverse design, where we optimize parameters for small scale meta surfaces and then we scale up for multi-objective type of problem?
Yeah, it's an interesting, right? It's an interesting topic, right? Because we are stuck with our computer is only, we cannot we cannot go to millions and millions and millions of parameters, right? So we end up in some situation where we have to make some kind of a sacrifice, where we try to make some smaller, optimizing something smaller and try to scale up. So it's, I guess that as far as I know, this kind of the standard way that's being done is using the inverse design of something smaller to scale up, or using some kind of tricks to segment specific parts of some meta surface and inverse design them step by step. But yeah, I don't know. There's a, if this is a nice research, it's a nice topic. If there's some way to simulate something small and scale up to something big, because again, what happens is, if we have some kind of neighbor interaction, we try to assume that each meta atom doesn't interact with anyone, but most of the time probably not true, right? So it's another thing that we should probably be trying to take care of, these interactions, these kind of neighbors and next neighbors and next neighbors. So when it gets big, these things should be included. It would be interesting. So those things are very, very useful. But then we have to care about how can we make how can we make it again when it gets big. Then can we even fabricate? We come back to a similar problem again. So we kind of have the battle of the can we fabricate, can we make it, and can we simulate it? Have these things. So it's an interesting concept. How we can scale up. I don't know too. It would be nice work.
Okay. Thank you so much for the explanation. Thank you.
Dr. Qasim, sir, one more question is online.
Um, okay, so I think Sumba, you have raised your hand.
Yes, sir. Hello, Dr. Trevon. Can you hear me?
Yep.
Yes. I would like to ask, where do you rate machine learning methods in current era in comparison with the deep learning methods? Are they being completely obsolete now or are in use?
You mean for material metaphotonics?
Yes. Yes, I mean in the design of metamaterials, meta surfaces, like you have explained in your talk.
I think so. I think that I wouldn't say obsolete, but I would say that in maybe 2019, 2020, it was a new method for inverse design or for designing meta surfaces or meta atoms, whereas now it's kind of a given. It's kind of just a tool. So I wouldn't say particularly obsolete, but I would say it's more of a tool that still needs to be refined. So similar to how if you go some years back, like designing, like making a meta lens was a big. You can make science or you can make some nature paper like this by making meta lens, but now we can teach to the first grade students. We can teach them very quickly how to make this. So I don't know if I would say obsolete, but I guess the knowledge is catching up, right? That is kind of a normal. It's not so fancy or something anymore, but kind of more of a just a tool rather than something super new. But what's interesting with AI is that it's always improving recently. So we keep improving. So if we can take some of these ideas from for example, guided supervised learning or the other parts of some of the things that the transformers that are inside large language models, somehow to put it into the design or into the system of metaphotonics could be very interesting, I think. But just basic
During
design.
deep learning. All right, thank you.
Is there some
Okay,
other
I have a
question?
question. Am I audible?
Yes.
Yes,
Am I
Sabir.
audible?
Yes.
Yeah, we can hear.
Okay, so I have a question regarding the application that you showed, which was about glucose sensing metasurface, about the integration of AI in metaphotonic systems. So, as we know, if we like do classification in normal AI, we have fixed classes as a result. Like if I train a network to predict one of the classes from like red, blue, green, it will predict one of them, right? But if we relate it to glucose it cannot be a fixed value. Some person can have like 98, one person can have like 9900 or something. So how do we deal with the interpolation, like if we have trained on specific points, how our metasurface is going to respond if we get a real time value in between those points? Can you understand my question?
Yeah, sure. So it's actually quite simple because we can do classification, but also we can just do regression, right? So we can do regression from 0 to 100, for example. And
Can
so
we make the metasurface do regression?
sure. But you mean for using the metasurface as as the network.
Yes.
Yeah. I don't know. No one did it. It would be interesting. Maybe it could be related to the intensity or something like this, rather than the location. But yeah, it would be
Okay.
interesting.
So we can
So
try something
I
about
don't know.
that.
But I guess there's no reason why not, right? There's no reason why it couldn't be regression. The output couldn't be regression rather than some kind of a classification.
Okay, thank you for your answer.
But maybe hard.
Oh, thanks, Trevon.
Hello,
And
Dr.
I hope
Trevon. Thank you for
we
such a nice presentation on conventional design and inverse design. I am a PhD student of Dr. Qasim. My name is Jamal. And I have a question which is circulating in my mind from last few weeks. That if we implement EM equations into a neural network, to visualize the results of a certain meta surface or maybe an antenna array, and will be feasible and less computationally complex as compared to the already available softwares like CST, HFSS, and other available softwares. So is it feasible to do that computationally? Because at the end, we are doing it for less computational requirements. So if we are not getting that, so there is no need of doing that. So I have this question in my mind, if you can kindly clarify.
Yeah, so that I kind of mentioned there that so in some I don't know if you know well, but in some other fields, for example, some kind of fluid dynamics kind of fields, there are some kind of a physical relationships, so related to the for example, the time derivative of some things. There's some kind of physical relationship that have to be true. So you can put this into your neural networks. So for example, the last two layers can be related to, they have to be physically true. And so we can incorporate this into the neural network loss function. And so, as you said, if we do this with nanophotonics or optics, it should probably become then to be including Maxwell's equations. But then if we are just solving Maxwell equations, we are just doing FTTD, right? We're just doing point by point FTTD. So I think it would be interesting to see how little physics we can put to make it improve. But as you said, if we put it completely physically, then we're just calculating Maxwell's equation. It's the same thing, right? So what you're thinking is correct. As I understand too, if you just put all of the physics inside there, you're gonna be just doing the same as a simulation. So you're not gonna get any upgrades. AI is not useful in the case, right? You're just modeling again.
Oh, thanks, Trevon. Actually, I told you the students will be very excited after your talk. So that's why so many questions popping up. So maybe I think we can take
It's fine.
1 to 2
It's
more
fine. It's fine.
questions. So Ramna, you raise your hand. So please go ahead.
Okay, hello, sir. Thank you so much, sir, for the nice presentation. I would like to ask the question regarding the inverse design. You have mentioned that in inverse design, we give our neural network some spectrum and then our network predicts some structure. So if our network predicts some random structure that is not according to our fabrication like resources, like it's not giving us the required aspect ratio or minimum feature size or spacing between the nano antennas, so how you could like deal with this situation?
So it's very important, right? So we can do inverse design, but it's pointless if we cannot make it. So if we have some 1 nanometer feature size, we cannot make it. So right, as you said, it doesn't make sense, right? So generally, what we can do is we have to do some kind of processing. So we do some blurring to maybe take away any feature sizes that are less than some 10 nanometer, 20 nanometer, we can add some kind of filters to the inside our functions, as well as another things we can do is we can we can code them inside, so that when we update, we can make sure that these are feasible before accepting this as one of our accepting this as the design. So we can incorporate all of that inside the loss.
Okay, sure, sir. Thank you.
Thanks. Is there any further question? Okay. Trevon, just
Right,
one quick.
right now from the physical audience, sir. Any question?
Physical audience.
Okay. Actually, there are a few people who joined online, and then rest of them are sitting in the lab. So,
Yeah, right.
okay. Trevon, just, comments on one thing. You see, as of now, all discussion is about conventional computational methods and replacing those with AI or physics-driven AI, so on and so forth. However, if we, you see, compare what's coming next, it's about how we can do like conventional. For the commercial solvers, there are very few options for quantum simulations, quantum computation, like quantum confinement, quantum entanglement, so on and so forth. And then your opinion about data-driven and physics-driven quantum computation. And obviously now people are also have been exploring the direction of, you see, meta surfaces for such kind of quantum confinements and quantum-like metal interactions. So where, I mean, you think that this idea will fit in the future perspectives, and what is the possible potentials in terms of this quantum computation thing?
I hope so. is my first things, because I want to go in this direction also. This is very interesting. I think so. At the current state, meta surfaces have been used for enhancing quantum emission. We did some work where we used this to structure quantum emission, and so some of the main important parts for like quantum computing or quantum photonics is related to the source, as well as the state manipulation, as well as the sensing and detecting. And it seems that meta surfaces have a very strong relationship to all of those things. So I hope that it's a very good direction to so like you said, instead of replacing conventional computing, it comes to quantum computing with photonic qubits or photonic, because the photon has many degrees of freedom. Actually, we don't need to use just qubits. Also, we can integrate, for example, multiplexing with meta surfaces for polarization, orbital angular momentum, wavelength, for example. So we could have a high dimensional quantum bit. I guess it's very interesting, I think.
Yeah. Okay. I think this is something which is futuristic, and the current conventional stuff has already been explored a lot, right? This is something which might carry enough potential for the upcoming few years. So
yeah.
Okay, thanks.
So as I just start my lab, that's what I have to think about.
Yes,
in the
yes,
10
yes.
years.
Okay, I think I will have a meeting with you on this, the way we discussed earlier, to see the possibility
Please,
of joining hands in this direction. You know, because few of
please.
my students, we started exploring this directions, and we are really hopeful that we can do something interesting, yeah, collectively.
Mm,
Okay, I think with this,
it'd be very
we will
nice.
wind up the session. We will wind up this session, and really, we are thankful to you for your time and for such an interesting talk. So everybody, let's thanks again to Dr. Trevon, and hope to see him sometime in Pakistan physically as well. We will try to invite him someday, or other way around.
Sure,
We
sure.
hope we meet him at some stage, at some conference. Yeah. Thank you so much, Trevon. So nice of you.
I hope so. Thank you. Bye bye. Bye bye. Thank you.
Okay. Bye bye. Bye bye.
Bye bye.